This is the math of how a rangefinder corrects for elevation. Here's a warning for this video. This is going to be a 4-part series, and each part is going to be pretty long with a lot of math. This video would be enjoyed by pretty much only somebody that likes long, complicated puzzles or scavenger hunts where every clue leads to another clue, where every piece of the puzzle will help you solve the next piece of the puzzle. And there's about 100 pieces in this puzzle. So it's a lot of math equations and a lot of detail. But if you're the sort of person that is curious and likes learning about the world, then this will have a lot of information in it you might like, providing you like the math. The math here will be pretty much just basic trig. And there's going to be maybe 3 equations from introductory physics, and they're going to be easy equations. It's just plug and chug. The part that really makes this difficult or requires the brain cells is that there's such a huge number of pieces of the puzzle that has to be put together correctly. So that's what took a long time. I made a few of these videos. Each time I make little errors, and I also make assumptions that I can't prove. So this time I intend to correct all of that. And I'm going to show every detail down to the centimeter or even the millimeter on how a rangefinder corrects for elevation when you're shooting up or shooting down. All right, so you're out in your big backyard or out at a shooting range, and you point your rangefinder up at something, maybe something up at a tall tree. That rangefinder is going to give you some information. Instead of a tall tree, it could be you could be pointing up or down a cliff. That rangefinder is going to tell you the distance. So example, 40 meters away, it'll say plus or minus 60 degrees. So you could be looking up 60 degrees or down 60 degrees. It'll tell you to use the 20-meter sight, which is half of 40. Here's the diagram that we're looking at right here. Here to here is 40 meters. Go up the circumference of the circle, so you stay 40 meters away from the shooter right here. This right here will form a hypotenuse if you're at a 60-degree angle. So alpha is the angle, 60 degrees. You take the cosine of this angle right here, 60, that equals adjacent divided by hypotenuse. Adjacent divided by 40 meters. So we got cos theta equals adjacent over height, or what this gives you is the distance, or it tells you which sight to use over the distance of the range. So bring the distance over, d cosine theta equals, or tells you what sight to use. In this case, 40 meters times cos 60 will tell you to use the 20-meter sight. So the sight that you use on your bow or gun or whatever will be this length right here. So it's a 40-meter range. Pretend you're shooting at something 60 meters away. Sorry, 60. Pretend you're shooting at something 20 meters away when you're aiming 60 degrees up. Again, I want to remind you that this video series is going to require a very long attention span and an extremely high amount of curiosity about the world and math and a love of complicated puzzles. I just felt like throwing that in there for redundancy. Okay, so the 4 parts here. You need the basic trig. This is all I'm going to use. 3 physics equations, plug and chug. This first video I'm doing is just the intro. The second video will be what happens when you shoot at something 0 degrees. Third video is when you shoot up at 60 degrees. Fourth video will be the math of when you shoot down at 60 degrees. And what I say here, I used extreme angles to get the near maximum effect from gravity. If you want the maximum effect of gravity, you're going to shoot up or down at 90 degrees, but that's not going to happen a lot. But 60 degrees is pretty darn steep. So that is a very steep hill, or if you're shooting up or down a cliff perhaps. I don't know if you could even really climb a 60-degree hill because you'd have to hold on to trees or something walking up, and if you got a lot of loose leaves below you. So anyways, this is pretty much unrealistically steep. If you are 40 meters away from your target and your target is at a 60-degree angle, say 60 degrees down, that means you're going to be up 34.7 meters high off the ground, or 114 feet high. I just took 40 times sine of 60 to get that number. So at 114 feet high, the average tree in a normal Midwestern forest is only going to be about 80 feet high to the very top branch. So you'd have to have your tree stand, say, halfway up a cell phone tower, or you'd have to be sitting up in some sort of giant redwood or sequoia. But again, by having this extreme angle, I really wanted to somewhat maximize the effect of gravity on how much it'll slow an arrow down when you shoot up and how much it'll speed your arrow up when you shoot down. And again, to fully maximize the effect of gravity, you need to shoot up or down at 90 degrees. I'm throwing this in as a quick explanation. Gravity only affects the velocity in the y direction. So if you have all your velocity tied up in the y direction, then you'll have the largest change from gravity. To get the vector, you do a squared plus b squared equals c squared. If you have no velocity in the x direction, that'll be 0. So if you have a velocity going shooting straight down at 100, add an extra 10 for gravity, now you'll be scoring 110, which will make the largest change. Shoot up at, say, 60 degrees, for example. There's the velocity, there's the vector of your arrow. There's gravity pulling it down. Your new vector will be here, though. That's the hypotenuse. Here's a squared, b squared, and c squared. We have a lot of velocity tied up in the x direction, so we won't get as big of a change when you do your Pythagorean theorem. Here's the diagrams. When you see all the equations and all the math I'm going to have to do, and plus to understand these diagrams I came up with, you'll understand perhaps why it took me maybe a couple of years to figure all this out. Granted, somebody that works in the field of engineering or physics would do this pretty easy because this is what they do, but I just figured this out for fun as an amateur. All right, so here's what the diagram would look like. If you're a shooter right here, you're shooting at 0 degrees, something 40 meters away. And in this case right here, it's still 40 meters away, but you're shooting up at a 60-degree angle. You're going to have to aim slightly above your target. So if it's a 40-meter target and you're shooting with a modern compound bow, you'll have to aim up about 1 meter high. Actually 1.2 meters high to be more accurate. So this comes out to be about 3% above your target compared to the x-axis here. So on the x-axis, the target's 40 meters away. You're going to have to aim up 3% higher than that for your arrow to drop back down and hit the target. Here's the exaggerated angles right here to get a better understanding. Shooter's here, target's there, arrow goes up in a parabola, hits the target right there. You have to aim up 1.755 degrees, which is 1.226 meters above your target, and I'll show how I got all these numbers. And that will compensate for gravity dropping the arrow down to right there. So this whole line here will represent the arrow drop, however greatly exaggerated, because in reality we're looking at a little area, a little distance right there that's 3% of this whole 40 meters. If you exaggerate this arrow drop here for illustrative purposes, we're going up 60 degrees to hit our target right here. That's 40 meters away. We have to aim up the same amount right here, the same 1.226 meters. And I'm going to show the math on how high to aim and all the details. So here's how we get our angles right here. This alpha right here will be the angle we're shooting up, say 60 degrees. This will be 90. Let's call this little tip right up here beta. I'm going to need to show yet another diagram to explain this, I think. We're shooting up at alpha. There's beta, there's our target right here. And then if this is alpha, that's beta, that's 90. Then if this triangle has beta and 90, then that has to be alpha. So here we have beta and 90. So this angle right here has to be alpha. So when you're shooting up or down at an angle and your rangefinder is using the degree, the cosine of alpha to determine what sight to use on your bow, it's not using the cosine of this alpha right here, it's using the cosine of this alpha right here. Here's alpha, here's the hypotenuse. This is the full drop of your arrow. And so we don't want to plan for that full drop of that arrow. We're only going to plan for this amount of drop. And if we're at 60 degrees, then the cosine of alpha is 1/2. So we only plan for 1/2 of the drop. So when your rangefinder gives you that number that says use your 20-yard sight or 20-meter sight, as if you're shooting at 0 degrees, let's go back down to 0 degrees. So instead of aiming for this full distance for the full drop of gravity right here, then we only aim for half of that distance, and the arrow will only travel half that distance. In reality, since we're dealing with gravity, if your rangefinder tells you to use the 20-meter sight, what it's doing is ignoring the fact that your arrow will slightly slow as it shoots up. If the arrow is slightly slowed from gravity, then it'll be in the air a little bit longer. You'll have a little bit longer of an arrow drop. If you're shooting down, the opposite happens. This arrow drop here becomes a little bit shorter. So when it compares this angle and compares the cosine to tell you what to aim for with your sight, so for example, to use the 20-yard sight, you'll actually slightly increase that distance when shooting up. So instead of aiming for 20 yards, you'll aim for 21 yards approximately, or 21 meters, because your arrow is slowed slightly. But if you're shooting down, gravity will speed up your arrow. So instead of aiming for the 20 meter or using the 20-meter sight, you're going to use the 18 or 19 meter sight, because your arrow will be sped up. Thus you can aim for a little bit shorter of a distance. So here's what we do here's what we got if I magnify this right here. And the top of it will look like this. There's our angle alpha, there's our angle beta, there's 90. So here we have 1.2 meter drop for which you plan for the arrow will drop this far from gravity. The arrow drop, or the vector for gravity drop, will always be vertical, no matter at what angle you are. So whether you're 60 degrees or 45 or 30, this gravity drop vector will always be vertical, because that's the direction that gravity pulls everything. So if we plan for the full 1.2 meter gravity drop here, then the bow can only use angles to measure it. A bow can't really, or the bow sights or a gun sights can't measure distance. They simply measure the angle between where the target is and where you actually aim. So in this case, your sights will tell you to only aim for half of this distance right here. So instead of 1.2 meters, you only aim for 0.6 meters if you're shooting up or down at 60 degrees. So it's 1/2 of the perceived arrow drop. And again, that just translates over here. So if you're shooting, what your rangefinder does is gives you a 0 degree shot as a reference. So even though you're shooting up at 60 degrees, it tells you that if you were shooting at 0 degrees, don't aim for that full distance, only aim for half the distance, about right there. This will be like a string on a stick. Think of like a fishing pole with a fishing line and a sinker right there. As this gets more and more vertical, this weight right here, this string, gets closer and closer to the stick. That cosine will decrease more and more. So you will have a shorter and shorter perceived arrow drop, and you'll use a sight that's sights that's for distances that are closer and closer to you. For example, if you're shooting up at 90 degrees and you use your 40-yard sight here, so you've got this, you're aiming up this high, you do that at 90 degrees, your sights are going to send the arrow off this direction and you'll miss the target. So this is why the more vertical or the steeper it is that you're aiming up, then the shorter the sight that you use. So if you're aiming up directly at 90 degrees, you plan for point blank shot as if the target is right in front of you. Point blank defined as no appreciable or no measurable drop in the projectile from gravity. Quick math on this. Like I said, I am showing the math on everything here and the proofs of everything. Here's the amount right here, 1.226 meters that you aim up, divided by 40 meters, gives you only about a 3% increase right there, and that's where you aim. And I just showed the math right there. 120. Oh, what I did here, I did 12 centimeters, so 120 millimeters from here to here, and then times 3%. That means I did 3.6 millimeters high to get that little mark right there. And this translates up here if you're shooting at 60 degrees. So you're actually not going to aim for this point right here. You're going to aim for that point right there. This diagram again just shows that if you're shooting up at 60 degrees, you don't aim for the full. This is where you aim if you're shooting at 0 degrees. This is where you aim if you're shooting at 60 degrees. You plan for half of the arrow drop from gravity. If you simply use cosine and do not consider gravity, this will still be extremely accurate. So a laser rangefinder, the one that I used, I just pointed up or down at anything. It just tells me to use the cosine of the angle. The formula I showed earlier, which is right here, it just gives this formula. Take your distance times the cosine of your angle. That tells you what side to use. This is actually extremely accurate if you don't consider gravity. But I'm going to consider gravity because I want to consider every detail down to the millimeter to make sure I have a complete understanding of this. And what I say here, arrow velocity will decrease when shooting up and your arrow velocity will increase when shooting down. So this will also increase or decrease the amount of time in the air, which will increase or decrease the amount of drop of your arrow from gravity. At 0 degrees, there will be no net gain or loss of arrow velocity. As you're shooting up here in a parabola, your arrow will slow as it goes up, but once it gets to the halfway point, it'll gain in velocity as it comes down, so you'll have no net gain or loss in arrow velocity, and that's at 0 degrees. Once you start shooting up or shooting down, that will change the overall velocity of your arrow ever so slightly. When I made my previous videos on this, I was making assumptions because I just wasn't very good at kinematics and this sort of complicated puzzle. But I intend to correct all that in this video where I go into the details down to, like I said, either the millimeter or the centimeter. Quick thing here, pretty much everybody understands. Increase the velocity of any projectile, you'll decrease the time in the air, and that will flatten your trajectory, so you'll have much less drop from gravity. Lasers, if you're shooting at something with a laser, you only need one sight because there won't be any arc and there won't be any drop from gravity. So whether you're shooting at something that's 80 degrees up or down or at 0 degrees, you just need one sight. You point the laser directly at your target. Rangefinder is really only needed for bow if you're using this for hunting. This is the logic I'm giving on this. I've never really heard of a hunter using a rangefinder for a gun because their trajectories are so flat, and when you're hunting, you're usually shooting at fairly close distances to make it an ethical shot. So a gun may target something 2 or 3 times farther than a bow. So if you're shooting with a gun, you might try shooting it at a deer 100, 150 meters away or so. So a bullet will travel, you can shoot at something 2 to 3 times farther, but the bullet travels 4 times faster than an arrow. So you're still going to have a flatter trajectory. From my experience, most hunting rifle shots happen in under 200 meters. I don't know what they do out on the plains or in the tundra where you could see for several kilometers. But I'm thinking if you have to use a rangefinder because you're shooting at something so far out, then yeah, it might not be the most ethical shot. I don't hunt personally, I just like ballistics. Okay, what I say here, ignoring air resistance, and first off, the air resistance won't be a whole lot with arrows or bullets when you're dealing with these shorter ranges. The coefficient of drag at all elevations is going to be the same, so whether you're shooting up, down, or 0 degrees. Granted, if you're shooting down, you'll get a little bit increase velocity, which will cause a little increased drag on your projectile, but that will be negligible. We have to break all of our velocities and distances apart. Gravity only affects velocity in the y direction, so break up all velocities into your x and y components, and same thing with your distances into the x and y components for the math. We'll have a velocity in the y direction initial and final to get the average velocity. And that's because gravity will only affect velocity in the y direction. Velocity in the x direction remains unchanged. Velocity, the average velocity in the y direction, this is what we use to get the time in the air, and then that's what we use to get the drop from gravity, because the longer it's in the air, the more arrow drop you'll have. I'll show the math on all the details. for somebody that's a little bit newer to trig, I would call this the shadow velocity. So for example, even though a projectile is going up here at 60 degrees to hit a target, we'll just pretend we're throwing a ball straight up in the air. And if there's a light right here shining in this direction or here, the light will shine and cast a shadow on the y axis. We're only looking at the velocity right here as if we're throwing a ball straight up and down. So it's like the velocity of that projectile shadow. And likewise, if we're looking at velocity in the x direction, just pretend there's a light shining down. And as this object moves up this way, we're going to be looking at the shadow of that object as it travels along this way. So that's why we break everything up into x and y components. Couple of distances here you don't want to confuse. I did this at first when I was trying to put all the puzzle pieces together. You don't want to confuse this distance with this distance. This distance right here will give you the angle at which to aim, and this will give you the velocity and the y direction. You look at the sign right here of this angle. This distance right here will tell you how far something goes up in the air, and then we use that to tell the amount of time that it's in the air, and then we use the amount of time that it's in the air to determine how far it goes on the x-axis. In other words, the longer it's up in the air, the farther it will travel. So this one gives us the velocity in the y direction. This one will give us the amount of time in the air. So two different distances, don't want to confuse them. I think that's pretty much what I said here. Angle, this angle will give you the velocity in the y direction. Velocity in the y direction will give you your distance of the p. I'm going to call this distance of the apex of the parabola. So we can use the velocity in the y direction to get this. And then we can also work it backwards. If we have this distance, then we can turn that into a velocity in the y direction. Distance of the apex of the parabola gives us the time in the air. The time in the air gives us the distance in the x direction. The equations we use for this are, for this one right here, velocity in the y direction, to get the distance to the apex of the parabola, d sub p. We'll use this equation from physics, the kinematic equation. And then for distance of the apex of the parabola to time in the air, we use this kinematic equation, 1/2 at squared equals distance. So these are the two physics formulas we need to know, plus distance over time equals velocity. Here's the logic, or the kind of the keystone on which all of these calculations are based. When you're dealing with these lower angles, if you only aim for half the angle, so instead of aiming for this whole angle of gravity drop, if you only aim for half of it, you're only going to get half the angle, or half the degree. Then this will give you 1/2 of the sine value right here. Then that will give 1/2 of the velocity in the y direction. That will give 1/2 the amount of time in the air, and then that will give 1/2 of the distance that the arrow travels. And it's because of this logic right here is why if you're shooting up at something 60 degrees, the rangefinder will tell you to use the cosine of that and use your 20 meter sight instead of your 40 meter sight. At these low angles, the cosine remains at almost 100%. So for example, cosine of 8 degrees is 0.99 or 99%. So if you're looking at this as a velocity in the x direction, all the way up to 8 degrees, you're still maintaining 99% of your velocity in the x direction. The angles that I'll be using are below 2 degrees. If you're shooting on flat ground, cos 2 equals velocity in the x direction over 80. Bring that over. That means we got a velocity in the x direction of 79.95. The 5 will round up to 9. The 9 will round this up. So basically we're looking at virtually 100% of our velocity in the x direction. If you take cos 2, you're going to get 0.9994, which is less than a 1/1000th difference in velocities. This works for the direct fire method of shooting at low angles, but if you get up to indirect fire for artillery or something, then it'll get more complicated, but I happen to like this right here because it makes for really much easier math. All right, that was just the intro. I've got 3 more videos now, and the next video will be the math of shooting at 0 degrees. The video after that will be the math of shooting at 60 degrees up. The next will be the math at shooting at 60 degrees down. So don't touch that dial if you're still interested.